more non-group elements. You can say oxygen, sulfur, selenium. Well, the metallic character is increasing, and the non-metallic character is decreasing. Okay, so from left to right, we can say that carbon is more metallic than oxygen because carbon is on the left side there, even though both are non-metals there. Okay, so metallic character, the periodic property for metallic character is also something that we want you to remember. So where would you expect to find, based on that general statement, where would you expect to find the most metallic elements in the periodic table? Top to bottom increasing, left to right decreasing. While the lower left corner will be the most metallic elements there. If you look at the periodic table, lower left corner, that is the element that's the most metallic, francium. Okay, so in this case, then francium would be atomic number 87. That's the most metallic elements in the periodic table. A similar type of question: where would you expect to find the most non-metallic elements? Well, you go back to the periodic table, excluding group 8A, fluorine, the upper right corner of the periodic table. That would be the most non-metallic elements in the periodic table. Now remember, when we were talking about the oxidation numbers in chapter 4, they say fluorine is always -1. Fluorine is the most non-metallic metal. Well, non-metallic elements in the periodic table. So fluorine will always take electrons from someone else. That's on the upper right corner here. Okay, so the metallic character has something to do with metal or non-metal properties there. Okay, so the conclusion that we draw here basically is that elements in group 6A, 7A. Well, why do you leave 4 or 5, 3 and 4 and 5 out? Those main group elements there. Well, there is a transition going from metal to non-metal. Okay? In group 4, group 5, group 3, we still have aluminum in there. Aluminum in group 3A, that's a metal there. So when we talk about the non-metal, we would say, well, group 6, 7A, group 6A, group 7A. Those are typical non-metals there. So elements in those two groups loses electron with great difficulty. They have very high ionization energy. If you try to take electrons away from them, they don't like it. Okay? And their negative ions are very stable. If you give them an electron, they become very stable. Therefore, they have high negative value for the electron affinity. So elements in group 6A and 7A, they form anions. They form negatively charged ions. And when they react with metal elements, and they form ionic compounds there. Okay. Now, group 1A and 2A, those are the main group elements there, metal elements there. The energy requirement to remove electrons from them is not as high. It's very low, actually. So negative ions formed for these elements are not very stable. They have very small negative value. It's a very low possibility as an exothermic process there. Okay. It doesn't release much energy there, and sometimes it may require energy in order to attach electrons to them. So they have small negative values of the electron affinity there. So elements in these groups will form anions, and they form positively charged. And when they form ionic compounds, they are going to be positively charged. Now, one group that deserves your special attention is the noble gas. In group 8A, they have no tendency to give or take electrons from one another. Matter of fact, all of these elements are trying to be just like them. So this is kind of like the cool group. Everyone is trying to be like them, have 8 valence electrons available. Well, nonmetals acquire the noble gas valence electron. Nonmetals acquires electron to get to the noble gas valence electron configuration. Metals loses electron to acquire that noble gas electron, valence electron configuration. So when metals loses electron, they get the same electron configuration as the noble gas on the previous period. Non-metal, when they gain electron, they get the same electron configuration for the noble gas in the same period on something that we want you to pay attention to. So, and in addition to metallic character, we also want to introduce, in terms of periodic property, we also want to introduce what we call electronegativities. D word, definition. How do we define electronegativities? Electronegativities is defined as the ability of an atom in the molecule to attract electrons toward itself. The general trend in terms of electronegatividity is that metals have very low electronegatividity. They don't want to attract electrons toward themselves. Non-metals, however, have higher electronegatividity. So in terms of the trend, remember this big arrow. How do we calculate, how do we assign electronegatividity? Well, Linus Pauling actually did a lot of calculations based on the number of valence electrons that we have, based on the core electrons we have there. This is the general trend. So going from top to bottom, electronegativity is decreasing. Going from left to right, electronegativity is increasing. So the most electronegative element, fluorine, the least electronegative element, francium, on the lower left corner. Very much similar to that metallic character here. So in general, electronegativity is increasing from the lower left corner across the periodic table to the upper right corner. And non-metals will have higher electronegativity, meaning they have a stronger ability to attract electrons toward themselves. So that's the periodic trend for electronegativity. And this is something that I want you to do. And this is a table, partially finished table. In terms of the moving through the periodic table, top to bottom, left to right, okay, what happens to the size, what happens to the ionization energy, what happens to the electron affinity, what happens to the metallic character, what happens to the electronegatividity. Finish this table after class and try to memorize that. I will ask you, I promise you, I will ask you questions in the third exam about the periodic properties. You need to memorize the general trend. And again, I'm only going to ask you, require you to know the general trend. I will not test you on the exceptions. However, when you're doing the homework, you may see exceptions on to those general trends there. And my philosophy really is, I always make the homework and the practice a little bit more difficult than the things that I'm going to test you. So that way, it's always a pleasant surprise when you look at the exam. Hey, this is not as difficult as the homework. So that's the idea there. Make sure you finish this table. Okay, and our last learning objective, and only a couple of slides left there, we give you another term that we call isoelectronic. And we need you to know how we define isoelectronic. And what does that isoelectronic mean? Okay. We need you to be able to demonstrate the knowledge of the term isoelectronic. Okay. And by defining and recognizing different species there. Now, by definition, isoelectronic is the term used for atoms and ions that have the same number of electrons. We're talking about the same number of total electrons. Okay? So in this case, determine the number of electrons for the elements will help you to determine whether two species are isoelectronic or not. And giving you an example here, nitride ion, N3-, nitrogen group 7A, nitrogen